At its core, mathematics applies strict geometric constraints to raw, chaotic numerical data and rapidly organizes them into a functional, readable grid. Linear algebra categorizes these grids into a strict taxonomy to manage complex systems efficiently. This classification relies on three pillars: the physical shape of the matrix, the dimensions of its order, and the behavior of its elements. Identifying a matrix's correct category provides immediate access to specific mathematical properties that are inherent to that form. Following this taxonomy enables the identification of structural patterns that would otherwise be obscured by the raw data. Within this 12-part classification system, we have arrived at the final and most strictly constrained form. These notes summarize the framework. Matrices are distinguished by their shape, their order, and the properties of their elements. This brings us to the anti-symmetric matrix. Its definition depends entirely on how its internal elements relate to one another. The anti-symmetric matrix exists in a state of balanced mathematical opposition. Every cell in this grid is governed by a single constant rule. By definition, a square matrix is anti-symmetric only if its transpose is equal to its negative. Mathematically, we express this foundational rule as A transpose equals negative A. To see this in practice, consider a standard 3x3 matrix labeled A. The transpose operation, A transpose, swaps the rows and columns. The horizontal rows rotate to become vertical columns. On the other side of the equation, the negative operation requires multiplying every single element in the original grid by -1. This formula defines the internal structure of the entire grid, determining the value of every cell based on its position. This rule creates a unique condition for the elements running down the center diagonal. We isolate these central cells to observe how they behave during a transpose operation. Because their row and column coordinates are identical, these diagonal elements do not change position when the matrix is transposed. While the rest rotates, these three cells remain stationary. This presents a problem. If an element doesn't move, yet the rule requires it to become its own negative, the element must satisfy the equation x equals -x. 0 is the only number that can satisfy this condition. Consequently, every element on a main diagonal is forced to be 0. In fact, the underlying formula leaves absolutely no other numerical possibility to exist within the dead center of the grid. But the elements existing completely outside of that locked center diagonal are forced to follow a totally different physical path. When the matrix is transposed, these outer elements swap their row and column index numbers. A cell in the top right moves to the bottom left. To remain equal to the negative of the original matrix, that value must flip its sign. This is the formal property shown here. A sub ij equals negative A sub ji. We can see this mirroring effect in the provided example. Across the diagonal of zeros, the positive 2 is paired with a negative 2, and the negative 1 is mirrored by a positive 1. The matrix functions as a mathematical mirror, where the grid structure dictates the algebraic relationship of its values. Viewing the document as a whole, we see how these components form a complete proof. The definition, formula, and numerical example are all in perfect alignment. This record illustrates how the visual arrangement of data points corresponds directly to their mathematical behavior. Recognizing this structural alignment is a foundational step in mastering linear algebra. There is a practical utility in identifying this specific anti-symmetric classification. It allows you to immediately determine that the sum of the main diagonal, a value known as the trace, is 0 without performing any addition. The summary notes confirm that understanding these distinct characteristics simplifies the broader study of linear systems. Understanding the internal mechanics of these grids provides a predictable framework for navigating complex mathematics.